Alrighty, let's go. Let's go. Let's wrap up chapter 12. So we're going to do 12.3. So we're going to start doing some calculus with polar because we just did a little bit of a lead in with polar just in case you were like me, not learn any polar before getting into calc 2. So hopefully that wasn't too much for you because now we're about to start finding derivatives. And we're going to find integrals soon, but we got to start off with derivatives. So we're going to begin with the fact that x is equal to r cosine of theta and y is equal to r sine of theta. In our big game, what we want to find is dy dx. Now, we had learned from parametric equations. Parametric equations, like didn't we have that it was, dy dt over dx dt? That was from parametric, yeah? Well, now we're not dealing with t's. We're dealing with thetas. The issue we have here, though, is we can't just find those two derivatives. It doesn't just work out quite that simply. It ends up being a chain. So let me just jump back to something. We've been dealing with r's and thetas, right? Instead of x's and y's. And I've been showing you that this is backwards from what we're used to, right? We're used to the fact you plug in an x and it gives you the y, right? The x is the independent variable. But in polar, theta is the independent variable. It determines how long the radius is. It's what works out the radius. It's the independent variable. Now, I don't know whether any of that really makes too much sense, but what we say is r is a function of theta. Therefore, when we go to find any sort of derivatives on this, we actually have, it's not a chain, I misspoke, it's a product. We have two functions being multiplied together. So let me get rid of all this stuff and let's actually go through and replace it because we're going to have to just do a little bit of work to build this formula, and it's not that bad. Let's say it's some function of theta, so that r is some function of theta times cosine of theta. Well, let's do the product rule. Let's go find our x prime. Okay. Cool. Let's check it out. Well, let's take a derivative on f first, and we just call it f prime of theta. That means we just leave cosine alone. And then next, let's just leave f of theta alone, and then we got to multiply by the derivative of cosine, which is negative sine. So, all right, cool. We got our denominator. There's our denominator. There's our x prime of theta. All right, that's it. I was going to say more. Really, that's all I need to say. So f prime of theta times cosine of theta minus f of theta times sine of theta. And now we're going to do the same thing over on the other side where we're going to go find our y prime, but we're going to say that this is some f of theta. So we're going to get times sine theta. Let's just write that in. So y prime is going to be, let's take a derivative on f first. That's f prime of theta, and we'll leave sine alone. And then we're going to leave the f of theta alone, and we're going to multiply by the derivative of cosine of theta. You all remember the product rule, don't you? I sure as heck hope so. It's not going anywhere if you're continuing on in mathematics. And there we go. It looks like we have ourselves a fancy new formula, huh? Look at that pretty little formula there. So let's scroll down and let's just go see what how they write it. And bang, there it is. Here's how we find the derivative, aka the slope of a tangent line. So as long as f is a differentiable function at theta naught, that's just a point, dude. Just a point. Typically theta naught, we're going to think of as 0. The slope of the line tangent to the curve at r equals f of theta at the point f of theta, comma. Theta is that big nonsense. Now there's a lot of stuff written in here and you might be getting a little bit overwhelmed, but it's a process, just like any of the other ones. Almost every time you get a theorem, it's going to have a lot of information on it because it's got to, as I call it, it's got to cover its ass. It's got to make sure that every little piece is taken care of. But it's not as bad as one would think. It's not. So let's start off with a quick problem. Let's just do one. So you're going to get a lot of questions that are going to say, hey, find the slope of the tangent line to the circle. All right, cool. Unless it gives you a point, that's just saying find the gosh darn derivative, huh? So let's go. Let's start with the simple one, just to make sure that we're all thinking like, man, this isn't so bad. So let's find the slopes of the tangent lines, tan lines, right, to r equals 10. R equals 10. Or you can think of it as f of theta equals 10. I don't know why I used the therefore symbol. That's not how you use that. Sweet. So in this case, f of theta is completely independent of theta. There's no theta there. So let's follow our formula. Okay. F prime of theta. That's freaking 0, dude. So let's plug it into our formula. We're like, all right, cool. Let's go find our dy dx. And we're just going to plug things in where they go. It says f prime of theta is our first thing we're going to plug in. 0 times sine. Ooh, this is rough. Then f of theta. Well, f of theta is 10. Times cosine of theta. Oh, all right. Just write in cosine of theta. There's nothing to do with it. That just is there. It is. There's nothing you can do about that. Now we're going to say, all right, took care of the top. Now go to f prime. That's 0 times cosine. Of course, that's going to go away. Minus our f of theta. That's still 10 times sine of theta. So as we can see, those just go away, and we're left with a 10 over 10. That goes away. So we just get negative cosine over sine, or cosine over negative sine, which doesn't really matter. It's negative cotangent. So it's saying that, the slope of the tangent line for any given value of theta is going to be negative cotangent of theta. But this was just a circle, right? R equals 10. I was trying not to say it, but R equals 10 is just a gosh darn circle. Right, it's gonna. Right, this would be at 10, 0 if we were in our x's and y's, but we're not. We're dealing with r's and thetas. Or we can think about it this way. We got our 0, we got our pi over 2. Sorry, that looks like an egg and not really a circle. In 2 pi. So we can find the slope at any place we want to, right? Don't we have a horizontal tangent line right there? Isn't f prime of theta equal to 0 right here? So what would happen? What would happen? So dy dx, and I'm going to use a little notation with you. Theta equals pi over 2. What would we end up getting? You can already see it. It's going to be 0. But cotangent is cosine over sine. Well, cosine of any odd multiple of pi over 2 is always 0, and cosine of pi over 2 is equal to 1, so we ended up with 0. Oh, weird. Well, let's try pi. Do you see it, pi? Sorry about my dog in the background. Hey, this is where our derivative is undefined. It's undefined. We have a vertical. Vertical, that's where the derivative, or we're going to have a 0 in our denominator. So we can say that our dy dx, and let's look at when theta equals pi. Well, that would be equal to negative cosine of pi. That's going to be 1. And then we have sine of pi, but that's a big issue. I'm going to write an equal sign, then I'm going to cross it out. This is negative 1 all over. Well, cosine of any multiple of pi is always equal to 0. So that's bad, right? We have, I can't even write that. You don't divide by 0. That's nonsense. So we found out where we had vertical tangent lines. That's not so bad. Also, there was no freaking thetas in there. It was just r equals a number. So we'll come back in our next one. We'll start messing around with a few more where we'll just ask questions like, hey, well, where do we have vertical or horizontal tangent lines? So we'll just do a little bit more. And then we're going to move into finding the areas. That's going to be the next thing. We're going to find areas of circles by using this. Or areas of cardioids, or areas of limaisons, or, I don't know, areas of polar stuff. But we're going to need to know how the graphs look, at least with the idea of symmetry. That's a good idea, because you don't have to know what all the polar stuff looks like, but as long as you know symmetry, you're going to be good to go, and I'll keep trying to remind you. All right, see you in the next.